Assalamualaikum and salutation to my panel, Dr. Khairul bin Kamaruddin and Dr. Zura binti Saleh. My name is Muhammad Amirul Mukminin bin Muhammad Ali, and in this video, I'm going to present my finding on this study. By the end of the presentation, I will describe the general information in my area of study in the introduction. In the methodology, I will describe briefly on the information required to obtain the result of the study. The finding of the study will be critically discussed during the result and discussion. And lastly, I will summarize the main finding of the study, restate the key points from the data observed, and discuss regarding the simulation. I will add some suggestions that should be included to encourage the continuation of the current research. Okay, for the introduction, what is gasification? With the help of figure 1, gasification is a thermochemical process that transforms carbonaceous material such as coal and palm kernel shell, which is going to be utilized in this simulation study, into syngas. Generated syngas can be directly utilized for heating and electrical power generation. There are many types of gasifier available, ranging from the simple to more complicated geometry. In this study, Dundra's gasifier was utilized, as shown in figure 2 for the simulation study. Dundra's gasifier is one of the fixed bed type gasifier that is most commonly used due to its easy fabrication, operation, and produce low tar content. For gasification fuel, coal is a reliable power source that is used for the gasification process. As a fossil fuel, coal is not a renewable energy, possess a finite supply, and also harmful to the environment as compared to all forms of energy and power production that the human use today. Hence, an alternative must be proposed to substitute coal as primary source of energy for gasification. Oil palm is an essential product that is enhanced the change in the scenario of agriculture and economy in Malaysia. The waste of the oil palm, such as PKS, is regarded as one of the potential renewable energy. By using gasification process, a potential technology which is capable of convert PKS into valuable fuel of syngas. Thus, I want to emphasize the present study critically observe and discuss the effect of different type of feedstock on the composition of the syngas produced using the simulation method. By reviewing the result of the simulation study, this study can identify the characteristic of syngas produced by PKS as compared to coal. After that, the suitability of PKS as substitution of coal for gasification fuel was then evaluated after the syngas composition, CO2 emission, price, and ability of PKS was discussed in this study as compared to coal. After the problem statement, objective, and scope are defined, the gasifier parameter and process data was collected during the geometry development. The fixed bed downdraft gasifier model was developed using SolidWorks. The geometry parameter was adapted from the previous research conducted by Liu, and the oxidation zone parameter was adapted from the Handbook of Biomass Downdraft Gasifier Engines. The model was exported as polysolid to ANSYS. The model was meshed using ANSYS mesh with the form of tetrahedron cells. The maximum phase size is set to 0.16 meter and the maximum tetrahedron size to 0.29118 meter. Inflation was applied to the model with the transition ratio set to 0.272 with the growth rate of 1.2. After that, the mesh is imported into ANSYS fluid for the fluid simulation setup. The species model was set to non-premixed combustion, and the fuel for the gasification was defined using the proximate and ultimate analysis. The simulation was run by using coal as gasification fuel as baseline for the study. During the simulation, the mole fraction for every syngas species produced during the gasification process is predicted by the console for convergence. The convergence criteria was set to 0.0001 in the unit of mole fraction for every syngas species produced during the gasification process. The simulation was initialized using hybrid initialization before the simulation was run. The simulation was run until the calculation of all monitor parameters are converged. After the calculation was complete, surface integral and XY plot was utilized to extract the syngas composition, temperature, pressure, and velocity data for the simulation process. The result of the simulation was compared with previous study conducted by Liu. After the error of the simulation study was defined below 25% for every syngas composition, the simulation was run again by using PKS as gasification fuel. The result from both simulations was discussed in the result and discussion according to the objective of this study. The findings are summarized in the conclusion, and the suggestions are included to encourage the continuation of the current result. For the result and discussion, the gasifier was meshed by using proximity and curvature as the size function for the meshing process, which contained as shown in the slide. The simulation was run first with coal as gasification fuel to validate the result with the previous study. The result of the gasification of coal are shown in Table 1. After the result of the simulation was obtained, the result from the previous research and the present study are tabulated in Table 2. The sets of data reveal the preciseness of the predictability of the simulation model. The error of the result of the prediction between the simulation are shown in the table. The comparison data with the previous study carried out by Liu et al. Reveal a good agreement with the present study, which shows the error did not exceed 25% for every species of syngas produced. The deviation of value between both of the results is caused by the different types of the species model used in the simulation process. The present study utilized non-premix combustion for the simulation process, while Liu et al. Did not specify the species transport model in their studies. This may cause the gasification to produce variation in the result of the syngas composition between both simulations due to the difference in simulating the transport model. By using the same parameter, the simulation was run again with PKS as the gasification fuel. The result of the simulation was tabulated in Table 3. After the result of both simulations was obtained, the data were plotted and shown in Figure 7 in the unit of mole fraction. During the simulation, PKS yield 52.29% less carbon dioxide. This is because during the pyrolysis of PKS, the carbon volatile reacts completely with oxygen volatile to produce carbon dioxide. PKS possess high oxygen volatile that causes carbon dioxide production during oxidation is higher than coal as shown in Figure A. During reduction, carbon dioxide reacts completely with carbon volatile of PKS to form carbon monoxide. This causes PKS to yield 90% more carbon monoxide than coal as shown in Figure 9. PKS has the advantage over coal due to it possess high concentration of oxygen volatile in its chemical properties as compared to coal. In contrast, coal carbon volatile did not react completely with carbon dioxide due to coal possess lower concentration of oxygen volatile. This causes less CO2 to react with carbon volatile in coal to produce carbon monoxide, which led to unreact carbon dioxide gas to be discharged at the outlet of the gasifier. Hence, this causes coal to produce 52.29% more carbon dioxide than PKS. The present simulation, PKS yield 53% more hydrogen gas than coal. This is due to PKS have a higher concentration of carbon monoxide that undergoes water shift reaction with water to produce hydrogen gas and carbon dioxide. This can be seen in the oxidation and reduction zone where the concentration of water decreases while the concentration of hydrogen gas is higher as compared to coal, as shown in figure 10 and 11. Although coal possesses a higher concentration of carbon volatile than PKS, the limited amount of oxygen volatile in coal hinders the carbon dioxide production during the oxidation of coal. This causes H2O mainly unused and exit as a product of the gasification process, which lead to coal to yield 71% more water than PKS. In order to study the suitability for PKS as gasification fuel, 4 criteria were discussed before suggestion to move from coal to PKS was decided. Those criteria are the value of combustible gas produced, the greenhouse effect, the price per metric ton of the commodity, and the availability of the fuel in Malaysia. As hydrogen gas, carbon monoxide, and methane gas have about the same energy density per mole when combust. The question is now, can PKS produce as many syngas as gasification coal can? From this table, this study can conclude that PKS produce 66.27% more combustible gas than coal. From the simulation, gasification of PKS released 944 parts per million of carbon dioxide gas, while coal released 1,496 parts per million of carbon dioxide gas to the atmosphere. By using PKS as gasification fuel, the concentration of carbon dioxide gas in the air can be lowered when the gasification process of PKS only releases 52% less carbon dioxide than coal. Figure 3 shows the trend of the price and the comparison of price per metric ton for coal and PKS. The data of the price of the commodity are obtained from the Australian Thermal Coal Price Index and Malaysia Palm Oil Board. Overall, the data reveal that the price of PKS is much lower compared to coal. Hence, PKS can be a viable option for fuel due to the low price than coal. Coal is widely available in Malaysia, but is PKS available in Malaysia? As we all know, palm oil production is vital for the economy of Malaysia, which is the world's second largest producer of the commodity after Indonesia. According to the Malaysia Palm Oil Board, Malaysia palm mill currently has an average of 12,000 tons of PKS in stock each year. Hence, PKS is readily available in Malaysia. After discussing the reason, PKS is suitable to replace coal as gasification fuel because PKS produce 66.27% more combustible gas than coal. Gasification of PKS only release 52.29% less carbon dioxide than coal gasification. The price of PKS is much lower compared to coal, and PKS is readily available in Malaysia. As for the conclusion, the present study proposed a gasification simulation of coal and PKS to study the effect of different types of feedstock on the composition of syngas produced using the simulation method. Comparison of the data with the previous study carried out by Liu et al. Reveal a good agreement with the present study, which shows the error did not exceed 25% for every species of syngas produced. The difference of syngas composition produced by coal and PKS depend on the chemical properties of the fuel. The different chemical properties of the biomass can affect the reaction that occurs during the gasification process of the biomass. This study also highlighted that PKS gasification produced 53.74% more hydrogen gas and 90% more carbon monoxide than coal when the gasification parameters are kept at a constant between the two simulations. Meanwhile, coal gasification produced 81.35% more methane, 71.31% more water, and also 52.29% more carbon dioxide gas than PKS. This study has discussed that PKS is suitable to replace coal as gasification fuel because PKS produces 66.2% more combustible gas than coal. Gasification of PKS only releases 52.29% less carbon dioxide gas than coal gasification. The price of PKS is much lower compared to coal, and PKS is readily available in Malaysia. Further research need to be done by applying different gasification agents such as pure oxygen instead of air to observe the syngas yield of PKS gasification. Then, by varying the diameter or height of the oxidation zone to observe the effect of the reaction that take place in the oxidation. It can affect the syngas composition produced. All this study can improve the syngas yield during the gasification of PKS. That is all for me. Thank you.